So this talk is about something I've called QEWD-JSdb, and basically what I'm going to try and get across is what is it and why should you be interested in it. And this is a shout out to someone who many of you know, Simon Legg, who in November put out a couple of tweets which kind of grabbed my attention. And for one reason or another, they just provided a focus to this work that I've actually been involved in for like 10 years now. And I've been kind of struggling with how to get the message across about what it is. And it was just in these two tweets that it sparked a thing. And this talk is the result of Simon, so I'm eternally grateful to him. So I want to talk about databases. In my view, in my experience, they're pretty much an unavoidable part of a back end of an application. And I just wanted to get a quick show of hands here about how many of you use databases, for example. How many of you have to access a relational database like Oracle or SQL Server? There's quite a few, Postgres and so on. How about document databases like Mongo, Couchbase? Yeah, a lot, yeah. Key value stores like Redis? Yeah, again, quite a lot. Graph databases. Anyone use a graph database? Yeah, a few. And finally, how many of you use multiple databases? You have to. Yeah, interesting. The thing about databases is there's so damn many of them. You know, every week we seem to see a new one. I've seen a new one lately called FaunaDB being tweeted about. You know, there's loads of choice with databases, as we've seen. There's loads of different models of database, and even within those models, there's a lot of choice. You know, do you go for Couchbase or Mongo or whatever? You know, relational, there's hundreds of them. And then the way you end up dealing with them in Node.js is typically over a network connection. So you've got the Node.js environment, one server, and you've then got your database over here at the other end of the network connection. And if you're really lucky, you've got multiple ones. And so you've got multiple guys to deal with across your network. So let's dig a little deeper into these database technologies and see what they're all about. You know, most of this is probably second nature to you, but I think I just want to build up a picture here, and I think it kind of creates an interesting message. So the main thing about why do you use a database in the first place? It's all about persistence, right? Your data stays there. You don't lose it when you switch off the system or when your code goes out of scope or whatever. You bring back the system and there's your data still there. Well, couldn't you just use a file for that? Well, arguably you could, but one of the features of a database is that you want to be able to query it or search it, right? And typically what you're trying to do is specifying a way of extracting a subset of the data. It's often known as a result set. You know, get me the addresses of all those subscribers in a particular area. If you're in medical work, you know, get me the names of all the patients under 20 with asthma, that kind of thing. And you usually express these queries either through a query language. If you're using relational, you'll probably be using SQL for that. But some of the other databases, you may use APIs instead to provide you the basis to navigate through the database to access what you need, and then you kind of marshal all the data and assemble it to meet the query that you're actually expressing. Third feature of a database is the model. And we've already seen there's a whole bunch of different models, you know, relational and so on. And that's all about how the data items are organized within that technology. So relational is one of the most common, of course, and in relational, the data is expressed as one or more two-dimensional tables with links between them, and typically the SQL query language to provide you with the basis to search across those tables. And then we've got these interesting databases known generically as the NoSQL databases. And we mentioned a few of them in the show of hands, your key value, document, columnar, graph. You've even got something called a native XML database. They're fairly obscure these days, but MarkLogic is probably the best example of that. And as part of the model, you typically have within the database a schema. You have to define a schema. And that will either be explicit, you'll have to define it explicitly, typically in a relational database you'll have to do that, or in some of the NoSQL ones, it's kind of implicit in just the way the data is organized anyway. You've got kind of no key value store as key value. That's it. So let's go back to that thing about a file. Could you use a file for this kind of stuff? Well, the main problem with a file, of course, is yes, you could, if you only had a few data records, probably be pretty fast, But if you've got gigabytes of data or terabytes or beyond that, then clearly a file just becomes nonsensical. You would have to load all that data into memory. You'd probably run out of memory in the first place. But, it just wouldn't work. So, and even within the databases, you need a way to avoid just exhaustively plowing your way through, a terabyte of data to find the result set that you want. And that then brings in the fourth feature of databases, which is indexing. And all databases will have some form of indexing within them. And they're there to provide you with an optimized way to get to the subset that you want without traipsing through the entire database. So why is there all this choice of databases? Surely the industry could have come up with a, one-size-fits-all way of expressing data. Well, to look at that, we've got to go back in time, really. And databases have been around for a long, long time. Some of you may be surprised to learn that they were around even before I started to become a developer. So pre-1970, really there were two types of database. There were the hierarchical ones. IBM had a thing called IMS. And then there were generically things called navigational databases. I won't go into what they're about. If you're interested, have a look on Wikipedia. General Electric had a database called IDS, and IBM had one called IDMS. And the IDS one became the basis of something called Codicil, which was an attempt in those days to provide a standard for databases. And then along came a guy called Edgar Codd, who worked at IBM, and in 1970 he published this paper, which was really a landmark paper. You should probably all go off and read it, actually. And it set the scene for the relational database model, where he said that this was a one-size-fits-all solution. You can express all your data as sets of two-dimensional tables, and then it was all about the calculus and algebra that would allow you to get the intersections of these or the unions and all this kind of, very, very much based on set theory. He actually produced a query language, but it wasn't adopted by IBM, funnily enough. They came up with something they called SQL, fully spelt out, and it was rebranded as SQL or SQL. And Larry Ellison from Oracle in 1979 decided to copy that. And then the rest really is history, because from the 1970s to 2009, relational just became the dominant database. I mean, there were plenty of products out there, but Ingres was one of the first. IBM had DB2, Microsoft SQL Server. Some of these are still around, some have gone. But really, the position was in that period of time. If you weren't using a relational database, you weren't using a database. Period. That was it. And then something very interesting happened in 2009. And that was this thing called NoSQL, and it burst onto the scene. Why did it do that? It was all to do with what was known then as internet scale or web scale. And this emerging view that these relational databases really just weren't suitable. They couldn't hack it for that scale of database and activity. For example, you needed something that could be fast moving and changing all the time. And once you're locked into a schema, it becomes very difficult with a relational database, particularly if you've got a lot of data mapped to that schema. To adapt that schema and change it becomes a real big problem. And also the performance of SQL, people were finding at this internet scale, the massive databases, massive number of users, the performance just wasn't up to the kind of level that people were needing. And so as a result, we saw the emergence of much simpler models and schema-free models emerging that could adapt very quickly to changing circumstances and so on. And also faster alternatives to SQL, so we saw things like MapReduce appearing, which really hadn't been around or certainly hadn't been used very much until then. Now, the interesting thing about this was, although the arguments about it were related to internet scale, where you've got, exabytes of data or, ludicrous scale, these NoSQL databases started getting adopted for normal scale, where you've got, megabytes of data or whatever. I would imagine a lot of you who are using these NoSQL databases, some of you might be on internet scale, but I would guess that some of you are fairly what I'd call normal scale. And it was interesting the way that NoSQL managed to break that monopoly of the relational world. And so here we are today with all this choice, all these different kinds of databases. Now, clearly how they all work will be different. Even if you take a relational model, how all the different relational databases work internally is going to be very different. And the proprietary ones, they'll keep that very secret how they actually work. But one of the interesting things is across the board, pretty much all are modeled ultimately on a hierarchical structure that underpins them. And a lot of them use something known as a B tree, which allows you to construct hierarchical structures on top. And here's one of the interesting things about databases, is that you can model any type of database on top of a hierarchical data structure. Okay? Now, the reverse isn't true. Once you've gone to some other model by abstracting from that hierarchical structure, you can't necessarily then model other databases on top of that. So if you like, the hierarchical model is the kind of Rosetta Stone database, the proto-database that you want to build any other database models on top of. Now, if you've decided to go for a particular database model, like a key value store or a document database or a columnar one or whatever, then it's fine so long as all your data requirements fit that model. It's great. It's perfect. If everything you need to do fits with the relational world, then that's great. But you end up often having to use these things inappropriately because your data doesn't quite fit. So here's Perl Scotties having to do a job with what he's got. Or you end up fighting it. You expend more energy trying to fight your database model to make it work with the data that you're dealing with than, so it just ruins your productivity. And as we saw in the hands before, what you otherwise end up with is having to go for multiple databases. So now you've got to deal with the learning curve and the support and the maintenance and management of several different database technologies just to meet your needs. And really, that's not ideal. And there has to be a better way, in my opinion, than having to deal with this kind of thing. So let's now forget about databases for a while and look at how you, as Node.js developers, JavaScript developers, handle data. You're handling data all the time. You know it as JavaScript objects or JSON. I'm going to use those two. I know there's a difference between them, but I'm going to use the two terms, JSON and JavaScript objects, kind of synonymously in this talk. You probably spend some time modeling data. In other words, you're, I would imagine, quite happy designing objects, JSON structures that fit your needs. You probably even create indexes for those objects, like using objects as hashes to provide pointers so that you can go directly to parts of your main data objects. So you're actually doing everything a database does, apart from two things. Your objects in JSON aren't persistent, clearly. They're destroyed if you go out of scope, or your process stops, or you turn off the machine. And of course, you're only dealing with small data sets. You're not dealing, you can't deal with terabytes of data in memory in a node process. But otherwise, you're dealing with data and you're effectively doing stuff and you're, I would imagine, perfectly happy doing all of those things. And so because you need that persistence and you've got a lot of information and you're only dealing with subsets, you have to do it this way. You need a database at the other end of a connection. And my guess would be that about 80% of your work is this. It's moving data from JSON into some other format. Maybe it's another JSON structure. Maybe it's some other structure you're marshalling your data into and sending it across through an API or a query or whatever to the database, which then saves it, and then the reverse. And then you're having to get what the database serves up in the format it serves it up and turn it into, marshal it into the structure that you want. And again, that's, should we really be doing that? Is that really what we're employed to do? So here's the suggestion. Imagine that you had objects, JSON, that were persistent, okay? Now, here's the interesting thing. JSON is inherently a hierarchical structure. Remember what I said? Any and all database models can be implemented on top of a hierarchical data structure. So from JSON, you could model any database model you liked. And you could design your data to work the way you want. You could implement the indices that you need, not the ones that you're stuck with. And you could even implement a query language if you wanted, write it in JavaScript, right? If you knew that you had, instead of this, you had this idea. So imagine you could get from JavaScript to either in-memory objects or to their equivalents on disk, as if they were pretty much the same things. And that's what the concept of QEWD-JSdb is all about. Okay, so how could that even be possible? How could you possibly do that? Well, of course, like everything in IT, it's always an illusion, and if you know how to create the right illusion, then you can do it. So how's the illusion created? Well, the first thing is it has to use a database. QEWD-JSdb does use a database because at the end of the day, you can't defy the laws of physics. You've got to have a database to do this. But the trick is that you need to have a database that's got some very specific characteristics. Essentially, the same characteristics of JSON. So what are those? It's got to be hierarchical, it's got to be schema-free, and it's got to be dynamic. In other words, no pre-declaration of anything. If you want to add a property, add a sub-object, merge stuff in, you should be able to just do that, okay? And there's not many databases around that can do that. The other thing is that what I call the unit of storage in that database has to be the individual key value pair at any depth within that hierarchy, not the complete JSON document. So you couldn't do what I'm describing with QEWD-JSdb with, say, MongoDB, where the unit of storage is a document, not the collection of individual key value pairs. And there's really only one database technology out there that meets these requirements. And you'll almost, I pretty much can guarantee you'll have never ever heard of them. I have, because I have the advantage of age, coming from a time when hierarchical databases did actually exist. And I've spent an entire career using these databases, and generically they're known as global storage databases. There are two main implementations around these days. There used to be lots, but it's all kind of filtered down. One is an open source one called YottaDB, and the other is a proprietary database called Iris. They used to have, there's a company called InterSystems. They used to have a product called Cache. Now they're marketing their product as Iris. These two products, although they look very similar, look very different, and you'll see them marketed very, very differently, Inside, underneath the covers, they are instances of this global storage database. So they're very little known. They date from the late 60s, early 70s. They actually dominate a couple of sectors. One is healthcare. Across the world, there are two major vendors of healthcare systems that hospitals buy. One is called Cerner, the other is called Epic. Epic uses Cache and are migrating to Iris. And they're a multi-billion-dollar company. They're massive, worldwide, pretty much dominate the healthcare sector. YottaDB is derived from, it's a fork of something called GTM, which has actually grown up around banking systems. So some of the major banks in the world, their core banking system, the stuff that you don't see, kind of the retail side, the internal stuff, is built on GTM, and YottaDB is an open source fork of that database. But as I say, the interesting thing is that I've yet to meet anyone really in these kind of conferences who's, oh yeah, I've heard of that, I've used that all the time. One of the things about these databases is they are incredibly fast, ludicrously fast. Even on this laptop, I could run Iris or YottaDB, and I could write or read is even faster, over 1 million key value pairs a second. Chris, my colleague who's here, he told me recently that he's been dealing with a very large Linux system where it's over 3 million. Is that right, Chris? Yeah. Yeah. I mean, these are near in-memory performance levels. And also, they are not toy databases. They have all the, the industrial strength. They've got the scalability. They've got all the management systems. You can replicate them and all that kind of, that just goes with them. So that's what I'm building on top of. So the way it's architected is that we've got Node.js over here with the JavaScript environment, and we've got the YottaDB or Iris database. First trick is, and this is courtesy of my colleague Chris, anyone who's interested in how this actually works, then talk to him later. We've got a connecting module called mgdbx, which creates an in-process connection. So this isn't a network connection. This is an in-process connection to a C-level interface that both those databases provide. So basically going straight into the core of the database engine at the lowest level. That's a very low-level API. So then the other thing that I've provided on top of that is an abstraction layer, which does this trick of then making these APIs appear to behave as persistent JSON objects, persistent JavaScript objects. And so that creates the illusion. Because it's in process, not across a network, because of that abstraction, you appear to have both in-memory objects and their on-disk counterparts. And you do everything, as far as you're concerned, you're dealing with JSON. Some years ago, it's actually soon after the whole NoSQL thing burst onto the scene, I wrote a paper with a colleague called George James about how this might be possible to map then these other databases on top of global storage. And this is what then was stimulated by those tweets from Simon Legg, was I decided, well, okay, the time has come. Not only do I provide the document database basic structure, I decided, okay, well, I'll build all these other database models, and I did that during November and December. So not only do you have the document database capability, you've got Redis-like key value store capability, you've got lists. I've even implemented a native XML database, which basically implements this persistent XML DOM. If you know the XML DOM, it's the W3C standard. It's an in-memory way of breaking down an XML document. It actually can be applied to any hierarchical structure you like, but an XML document into a document object model. It's got a counterpart, the HTML DOM. You'll all be familiar with get elements by tag name, get elements by ID, create element, and all that kind of stuff. That's the DOM. And normally it works in memory. In this, it works on disk. Okay, so it's effectively saying, well, let's just have this XML document persistent. And I've plugged in XPath querying. And here's the really cool thing about the XPath querying is that I took the standard Node.js XPath module, which expects an in-memory DOM, and I just plugged my on-disk DOM into it, and bang, it just worked. It was fantastic. And so I didn't have to worry about writing an XPath parser or whatever. I just plugged it in, and I'll show you later, I think we've got time, that it does actually work. And again, courtesy of Chris, my colleague, I've also implemented a relational model as well, and with SQL. And so at the same time, you can have relational databases modeled on top of this. So I've done this really as a showcase to show what's possible, that these things can be done, but also then you can take this and you can build on top of it whatever other models you want. For example, I'd love someone to do a graph database on top of it. That would be, I wouldn't say it was very straightforward. Structurally, it would be straightforward. Like all these things, it's the querying that's the problem. So let's start with this guy here. What I've trying to do here is to demonstrate a few of the capabilities. So on the right here, I've got a browser-based application which allows me to play around with the basic JSON storage. So here I've got just this example JSON. And over here, in this area, you're seeing a view in real time. There's a WebSocket application on the left, which is waiting for changes to occur within the actual global storage database. And as soon as it changes, it's going to render it and show you what's in there. So I could take this object here, and I could say set document. Bang, there it is. It's taken that JSON, and it's mapped it into the database. And here's the hierarchical structure that it's created. And if I scroll across here, you'll see the JSON abstraction of it. So I could retrieve that. This is basically retrieved that in real time and displaying it then as the JSON. And it's exactly the same JSON that I put in. And here it is. Oops. Now, if you look at this hierarchy, you'll see here, these are the what are called subscripts in the database, and they map one-to-one onto the keys of the JSON. So it's actually this very nice one-to-one mapping that it just gives you automatically. So for example, I can say get document here, and it'll pull back there. That's pulled it all back from the database again. I can then, but I don't have to just go for the entire object. I can pull out sections. So if I click on this, it's going to just give me this section here, the contact section. And there's that subset. I can drill down further, go down to the next level, the next level, and the next level. And you can see I'm just down to this subset. So you've got random access to the JSON in storage. You're not having to pull an entire document off the disk and into memory and manipulate it. This is manipulating, pulling directly from the disk and creating just the subset that we want. I could delete a section, so I could say let's just get that main view back again. If I say get document here, sorry. If I do that, that'll bring back, there's the whole thing. And you'll see here, we've got subscripts like demo contact, okay? So I could say here, delete demo.contact, and bang, it's gone. See, it's disappeared. What else have I got down here? And I can add stuff. I could add hello world. Oh, sorry. Hello world. And I could say I want to add that to demo.abc. And bingo, there it is. It's added it up here, you see, just like that. So that's all very well. So now let's have a look at lists. So this is a Redis-like list API. So let's just clear down that view in there. And I can say, so this is going to come up with test data here. Every time I add an object onto disk, it'll bring up another record. So I've got a few canned kind of records. So here's mine, first name, last name, city, gender. And I can say, right, I want to, I don't know if you know Redis lists. You've got lpush and rpush and lpop and rpop, stuff like that. So let's do an lpush, bang, and you'll see what it's done here with that, just that expressed through that API. It's created a data structure from this record that is providing me with the linked list, so that if I do another lpush and another one, then you can see you've got these previous node and next node pointers, so that when I do I can do an lpop, for example, and it'll pull me back that record and delete it from the database. Or I could do an rpop and it'll get it from the other end of the list. So that's all very interesting. You can play around with that. How about the relational database? So I can clear down that again. And again, same idea. I've got these test objects that are going to, I can add into the thing. So I'm going to create a table, and this is going to use SQL. So it's going to use a create table SQL command to create the table. That's created that. And let's create an index. I'm going to call it by city. And oh, sorry, wrong way around. It's the city field, and I'm going to call the index by city. So let's create that index. And now I'll insert a record. I'll insert another record, insert another one. And you can see they've been added into the database here. That's using SQL inserts. And now I could get them back, select star from this guy. Oops, it didn't work. That didn't work. I'm not quite sure why that didn't work.
The index looks empty.
Oh, there it is. There it is. There it worked. Sorry, I don't know what happened there. So there it is. It's pulled back the records, the result set, with all the fields. I could be some more selective. I could say select last name, where city equals Red Hill. Okay, it's not playing ball, that. I don't know why. Why isn't that happening? Not quite sure why. Oh, there we are. There we are. And there we go. It's pulled back the records where the last name was Red Hill. So we've got, and I could do the delete as well. Let's have a look at the XML DOM. This one's my favorite, most spectacular. So here I've got an XML document. It's all about pubs. And let's clear down the, why is that not clearing down? Let's just reload that. Okay, and there we are. Okay, so I'll parse as XML. Now the parsing uses the standard Node SAX parser, and then it uses the XML DOM APIs that are implemented in this to save the records as it does it. So it'll parse the document. There it is. It's parsed that entire document, and now it's representing it as effectively as a persistent DOM. But the way you access this then is through the APIs, the DOM APIs, which are all implemented exactly as per the W3C spec. So for example, first thing I can do, I can output that XML again. There it is. It's retrieved it as XML. Okay. I could do this. I could put a tag name, foo, and it'll do get elements by tag name. And back it comes. Here are the nodes there are the foo nodes. Get element by ID. I could put an ID of unwins. Get element by ID. There it is. It's found that in the document. I can also run an XPath query. I could say // foo, for example, run the XPath, and there they are. There's the foo nodes come back through XPath. And as I say, that's using this standard Node.js XPath module, which assumes it's an in-memory implementation. It's actually getting it off disk here. It just doesn't know the difference, can't see any difference. We can even do something really cool here. If I've got a few more minutes, Adam?
We've got about 3 more minutes.
3 more minutes, okay. What we can actually do here is dynamically build an XML document off this. So I could say, I'll start with the document tag, and I'll say that it is Rob. Append the element. It's added it to the DOM, and if I go up here and I say output as XML, there we are, it's coming back as Rob. And now I could go down and I could say what I want here is // Rob, and I'm going to append a tag called hello with a piece of text inside world, and append that element. It's added that into the DOM, and I can go up here and output it as, and there we are. It's all, and that's on disk. So you could use this to dynamically build on disk, directly on disk. This isn't going through memory, this is physically writing it to the disk as an XML DOM. So that is JSDB. If you're interested in it, have a look on the GitHub site. It's all open source. If you use the YottaDB version, it's all open source, free to use. All the code is there. It's all Dockerized, the lot. So just give it a try. And that's JSDB. Hope you find that interesting. A good way to start the decade.